Welcome to the video Help with Physics problems for Physics 1B. In this video we're going to cover Homework Set 1, Part 1. That's everything under the headings, electric charge and Coulomb's law, and the electric field. For 1221 students, this is questions 1 to 4, and for 1231 students, this is questions 1 to 7. Problem 1. In this problem we have 2 point charges, plus Q and plus 4Q, which are a distance L apart. We place a third charge to make the entire system in equilibrium, and we need to find the location, sign, and magnitude of the additional charge. Let's start by imagining that we place a charge Q off the axis joining these two charges. Well, in that case, as these two charges both have the same sign, it's either going to be attracted to both of them or repelled from both of them. So if we draw the forces, let's assume that it's attracted, then these are going to have a y component, which is going to cause this charge here to move towards the line joining these two charges. So that can't happen because we need the system to be at equilibrium. So that tells us that we must have it somewhere along the axis joining these two charges. Now if we put a positive charge here, it's going to be repelled from this one, and so it'll move off. Also, if we put a positive charge here, it'll be repelled and move off. So that can't happen. Now, if we put a negative charge here, it'll be attracted to both of these and move to the left. And if we put a negative charge here, it will move to the right. So that tells us that the charge must be placed somewhere between these two. So let's place our charge, capital Q, a distance x from the plus Q. And now what we can do is we can work out what x is and what Q is. Okay, so to be in equilibrium, it means that there's no force on any particle. Okay, so let's consider plus Q first of all. The forces on the charge plus Q. Well, they all come about due to Coulomb's law. We've got the electrostatic repulsion or attraction to this capital Q charge, and we've also got the electrostatic repulsion or attraction to the charge plus 4Q. So we just need to add those two together. So we've got the 1 over 4 pi epsilon naught, and then Q over the distance between these two is x squared, and then we've got the force between these two, which is Q times 4Q over the distance between them, which is L squared, and we know that that has to equal 0. Let's call that equation 1. Now we can also work out the force on the plus 4Q particle. Okay, it's got the force between itself and this capital Q, so that's 4Q over Q, and the distance between these two, if this is L and this is X, then this distance must be L minus X. And then we've got the force between plus Q and 4Q, so that will be 4Q squared over L squared. We know that equals 0, and that's 2. Okay, now what we need to do is solve these simultaneously so that we can get X and capital Q. So we can cancel off these as they're equal to 0, and 1 will tell us that Q, big Q on X squared is equal to 4Q squared on L squared, and so cancelling off this Q and this Q, we have there's a negative there, because this whole thing here must be equal to 0, and so we have Q is equal to 4Q x squared over L squared, and there's a negative sign there, and we know that Q is positive. X squared, L squared and 4 are all positive because they're all squares, so we know that the sign is negative. It must have a negative sign. Okay, now 2 we can rearrange in a similar way. This whole thing here must be 0, so we have 4qq on L minus x all squared is equal to minus 4q squared on L squared, which tells us that q is equal to, cancelling off those little q's, and we can cancel off these 4's as well, it's equal to q over L squared, we've still got the negative sign, and then that's L minus x all squared. Okay, so now what we can do is solve these two simultaneously. So we've got 4qx squared on L squared is equal to q over L squared, L minus x squared. We've left off the negative signs as they'll cancel out. The q's will cancel out, the L squareds will cancel out. We have 4x squared is equal to L minus x all squared. Now, 4 is a nice square number, so let's go up the top here now. What we can do is take the square root of both sides, and we have 2x is equal to L minus x. Now, x must be a positive number because we said that if it was on this side, then there would be a resultant force. And L minus x is going to be positive as well because L's positive and L is bigger than x. So that the signs are okay. We don't need to change one of the signs. And so we have 3x is equal to L, so x is equal to L on 3. Okay, so we've got our location now. We're a third of the way along. All we need to do now is work out the charge, so we can substitute back into this equation. Q is equal to minus 4q x squared, which is L over 3 squared, times 1 on L squared. Okay, so this is minus 4q, and this is over 9, taking the 3 squared, L squared on L squared. Those just cancel, and so we end up with minus 4q on 9 is our charge. Now, the question asks, is the equilibrium stable? Stable equilibrium means that if we perturb it a bit, that's if we move it a bit to either side, it will go back to its equilibrium position. In this case, if we move a negative charge a little bit here, it's then closer to this charge, and so it's more attracted to this charge than this charge, and so it will accelerate towards this charge. So that is an unstable equilibrium. If we were to perturb it in the opposite direction, it would be attracted to this charge over this charge and would accelerate towards this charge. So once again, it's unstable. Okay, problem 2. In this problem, we've got charges hanging from light threads. So they form an angle theta, this is theta, with the normal, and we've got their weight force mg because they've got a mass m, we're told. We're told that the length of this string is L and the distance between the two charges is x. So all the forces involved, we've got the weight force acting down, we've got the tension forces acting upwards, and then we've also got the electrostatic repulsion. Because they've both got charge plus q, they will repel each other, and so we'll have a force in this direction. Fq is equal to 1 over 4 pi epsilon naught q squared over the separation, which is x squared. Okay, and what we're asked to do is find an expression for x here, and we're told that we can assume that tan theta is approximately equal to sine theta as theta is small. So to answer this, we actually need to consider the geometry of a couple of things. One, how the forces are related, and then secondly, how these distances are related. So let's draw a diagram showing all the forces. We've got the weight force mg acting down, then we've got the electrostatic force here, which is acting perpendicular to the weight force, as we can see from this diagram. This is 1 over 4 pi epsilon naught q squared on x squared, and then we've got the tension force acting up here, which makes an angle theta, as we can see, with the normal here. So this diagram, this force diagram, tells us that tan theta is equal to opposite over adjacent. So that's 1 over 4 pi epsilon naught q squared over x squared over mg. So there's an mg on the bottom there. So that's the expression that we've got from this diagram. Now, if we consider the geometry of these distances, this distance here is x over 2 and this distance is L. So we've got an opposite and we've got the hypotenuse. So this diagram here tells us that sine theta is equal to opposite x over 2 over hypotenuse, which is L. So we've got sine theta is equal to x over 2L. And we've been told that we can approximate tan theta is approximately sine theta. So what we can do is say x over 2L is equal to 1 over 4 pi epsilon naught q squared over x squared mg. Okay, we can cancel off our factor of 2 there. And what we're trying to do is get an expression for x. So we can move the x squared up here. So we've got x cubed is equal to lq squared over 2 pi epsilon naught mg. Okay, so to get x, we just need to take the cubic root. So we've got lq squared over 2 pi epsilon naught mg to the power of 1/3. And that is indeed what we were asked to show. Okay, then in part B, we're told that L is equal to 120 centimeters, so 1.20 meters, and M is 10 grams, so 10 times 10 to the minus 3 kilograms, and X is 5 centimeters, so 0.05 meters, and we're asked what is Q. Okay, so we can write Q squared is equal to, just rearranging this, we've got X cubed times 2 pi epsilon naught mg all over L. All we need to do is substitute in, so 0.05 cubed times 2 pi times epsilon naught, which is 8.85 times 10 to the minus 12, and then times the m, 10 times 10 to the minus 3, and then times 9.8, and all over L, which is 1.2. Solving this on the calculator, we end up with 5.676 times 10 to the minus 16. This is Q squared, so taking the square root, Q is equal to 2.38, which to two significant figures is 2.4 times 10 to the minus 8 coulombs. So that's the answer to B. Okay, problem 3. We have 3 charges in an equilateral triangle. So we've got plus Q up here, and then here we've got a minus capital Q, and here we've got a plus capital Q. And we're asked, what is the direction of the force on plus Q? Okay, well, the force between plus Q and plus Q is going to be repulsive, so it's going to be in this direction, and it'll be along the line joining these two. And it'll have a magnitude 1 over 4 pi epsilon naught QQ over whatever this distance is. It's equilateral, so let's just call that x squared. The force between plus Q and minus Q, this is going to be an attractive force. It will end up with the same magnitude, as the distance between these two is the same. It's an equilateral triangle. It's just going to have the opposite sign because of this opposite direction. And so if we broke these into horizontal and vertical components, the vertical components are in the opposite direction, but they have the same magnitude, so they cancel out. Whereas the horizontal components add together. And so the total force is going to be in this direction here. So to the right and parallel to the axis joining plus Q and minus Q. So to the right and parallel to the axis joining plus Q and minus Q. We could actually work out its magnitude as well, as we know this is 60 degrees as it's an equilateral triangle. So this is 60 degrees and this is 60 degrees. And so the horizontal component is equal to cos 60 times 1 over 4 pi epsilon naught QQ over x squared, where x is the side length, A is the side length we're told in the question of the equilateral triangle. And so cos 60 just using our special triangles. If that's 60, then this is 1, this is 2, this is root 3, so cos 60 is 1/2. So this is 1/2 times 1 over 4 pi epsilon naught q on a squared, replacing our x squared here with a. And so that tells us that because both of these have the same horizontal component, the total force is double this, so we can get rid of this half. It's 1 over 4 pi epsilon naught q over a squared. Okay, problem 4. In this problem we have two charges. Let's call them Q1 and Q2. Q1 has a charge of plus 2.0 times 10 to the minus 7 coulombs, and Q2 has a charge of plus 8.5 times 10 to the minus 8 coulombs. They're placed a distance 12 centimeters apart. And part A of the question asks, what electric field does each produce at the site of the other? So the electric field produced at Q2 due to Q1, so we'll give it a subscript Q1 saying it's due to Q1, is going to be given by our formula for electric field, 1 over 4 pi epsilon naught q over the distance squared. So this will be 1 over 4 pi epsilon naught Q1 over 0.12 squared. Substituting in, we'll end up with 1 over 4 pi times 8.85 times 10 to the minus 12 times 2.0 times 10 to the minus 7 over 0.12 squared. Solving that on the calculator, we get 1.249 times 10 to the 5 newtons per coulomb. And as everything's given to two significant figures, let's write this as 1.2 times 10 to the 5 newtons per coulomb. Now, this is a vector, so it needs a direction, so the direction will be like that. But we can describe that as directed radially outwards from Q1. Okay, now to get the electric field at Q1 due to Q2, we do it exactly the same way, except that we're using Q2 now instead of Q1. So we substitute in the same here, except that we replace this 2.0 with an 8.5. So when you replace this with an 8.5 times 10 to the minus 8 and solve it on the calculator, you end up with 5.31, so 5.3 times 10 to the 4 newtons per coulomb, and that's directed radially outward from Q2. And you could also say it's directed along the axis joining these two. There's many ways to describe that direction. Part B, what force acts on each? Well, they're going to exert an equal but opposite force on each of them. So we can use the equation F is equal to EQ. So the force on Q2 is the electric field at Q2 due to Q1 times Q2. So let's do it that way. It's E Q1 Q2. So that is equal to, keep all the significant figures for the working, 1.249 times 10 to the 5 times Q2, which is the 8.5 times 10 to the minus 8. So that gives us 0.0106 newtons, and so to two significant figures that's 0.011 newtons, and this is a repulsive force. So saying that it's repulsive gives its direction. Q2 feels a force this way and Q1 feels a force that way. Problem 5. This is for 1, 2, 3, 1 only. In this question we have a square set up. We've got a charge up here of magnitude plus q, a charge over here with magnitude minus 2q, Down here we've got our charge plus 2q, and down here we've got a charge minus q. The distance between each of these is a, and it's a square, so all those distances are the same. Now in the middle of the square we have a point P, and we're asked what is the magnitude and direction of the electric field at P. And we're told we can have A is equal to 5.0 centimeters, so 0.05 meters, and Q is equal to 1.0 times 10 to the minus 8 coulombs. Okay, so what we need to do is just consider at P the electric field due to each of these charges, and then we can just add them together. Now, due to the plus Q, that's going to be directed along the line joining plus Q to P, and the one from minus Q will be directed along the line joining minus 2Q and P. So these are actually at right angles to each other. So we can imagine these lines through the center of the square as a new set of axes. So let's just label our axes. Let's call this one the alpha axis and this one the beta axis. Okay, so we can write down the electric field due to each of the charges. The electric field due to the plus Q is equal to 1 over 4 pi epsilon naught, and then the charge is plus Q over the distance. Now, this distance here, we've got a triangle that's 90 degrees. These are equivalent. This is A. So let's let that be X. That's X then. So we've got X squared plus X squared is equal to A. So 2X squared is equal to A squared. That's just Pythagoras' theorem. And so X is equal to A over root 2. Okay, so this distance along here is A over root 2 for each of those. So we've got over the distance squared, so that's A squared on 2, so we can put the 2 up the top. And this one here is in positive alpha direction. Okay, now let's consider this other electric field in the alpha direction due to the plus 2Q charge here. So the electric field due to the plus 2Q is equal to 1 over 4 pi epsilon naught plus 2Q. And now the distance is once again A squared on 2. So we can put a 2 up the top. 2 times 2 is 4. So we can make that into a 4. And this is in the minus alpha direction. Okay, now let's consider the electric field in the beta direction, so due to these minus Q charges. So this one, the electric field is going to be directed in this direction. So E minus Q is equal to 1 over 4 pi epsilon naught minus Q over, now the distance separating them is once again A on root 2. So this is A squared on 2, and the on 2 goes up the top. And this is in the negative beta direction. So this negative here is taking into account that negative there, so maybe we'll just make that in the positive beta direction. It's going this way. And then for the minus 2Q, it ends up going in this direction, and so we've got E of minus 2Q is equal to 1 over 4 pi epsilon naught minus 2Q over A squared. Now this is A squared on 2, so we put the 2 up the top and we end up with a 4. And that is in, well, let's make this a positive, and it's then in the positive beta direction. So these two cancel out a bit and these two cancel out a bit. So in the alpha direction, we've got a total of, this one's double that one, and they're in the opposite direction. So we've got 1 over 4 pi epsilon naught 2Q over A squared, and that will be in the negative alpha direction. And these two, this one wins, it's bigger, so that's the positive beta direction. They're equal to 1 over 4 pi epsilon naught 2Q over A squared in the positive beta direction. Okay, so now we've got the electric field, we've got it along our two perpendicular axes. Now all we need to do is add these vectors head to tail. So this is in the negative alpha direction, so this is going up like this, and it is 1 over 4 pi epsilon naught 2q over a squared. And then this one is going in the positive beta direction, so up like that. These are at 90 degrees to each other. This is 1 over 4 pi epsilon naught 2q over a squared, so they have the same magnitude. We add them together. This one has a horizontal component to the right, and this one has a horizontal component to the left. So those horizontal components cancel each other out. But we can just use Pythagoras to work out our total answer, and we can see that it's going to be vertically upwards as the horizontal components are cancelling each other out. So when we do this squared plus this squared and take the square root, it's 2 times this all squared, so it's root 2 times whatever this is. So it's 2 root 2q over a squared times 1 over 4 pi epsilon naught. So that's our answer, but we were given some values to substitute in. So let's do that now. So the electric field is 2 root 2 q, which is 1.0 times 10 to the minus 8 over a squared, which is 0.05 squared, times 4 pi times 8.85 times 10 to the minus 12. Solving that on the calculator, you get 1.02, but everything's only given to 2 significant figures. So let's put that as 1.0 times 10 to the 5 newtons per coulomb. And the direction is pointing directly upwards. This is our direction here, so vertically up the page. Okay, that's that one. Okay, problem 6. Which is for 1, 2, 3, 1 only. In this problem we have a dipole, so we have a charge plus q here and a charge minus q here. We're told that there's a distance a between them, and then we imagine a point, say P, which is at a distance r from the centre of the dipole. So that distance from there to there is given by r. And we're asked to derive an expression for the electric field in this case. Okay, so the electric field comes about due to the sum of the electric field generated by the plus q and by the minus q. So let's consider both of these separately. We've got 1 over 4 pi epsilon naught. Now due to plus q, the charge is q, positive q, and the distance between this charge and this charge, this distance from here to here is half a, so that's a on 2. So the distance is given by r minus a over 2, and that's all squared. And then we need to add on the electric field due to this minus q charge. So that's 1 over 4 pi epsilon naught. Now I've got minus q is the charge, and the distance in this case is equal to r, that's the distance r, and then we have to add on an extra a on 2. Okay, so let's add these two together. We've got q over 4 pi epsilon naught outside of 1 over r minus a over 2 squared minus 1 over r plus a over 2 squared. Okay, so this is q over 4 pi epsilon naught. Let's give it a common denominator, r minus a over 2 squared, r plus a over 2 squared. Okay, so this term goes up here, so we've got, let's expand these brackets when we move it up. So we've got r squared plus 2 times r times a over 2, so that's ar, plus a to the 4 over 4, and then we have to minus this thing, so that's r squared, minus minus, so that's plus ra, minus a to the 4 on 4. Okay, now we're told that r is much bigger than a. So let's make use of that now. We've got q over 4 pi epsilon naught. Now, the r squareds here cancel out. The a to the 4's cancel out, and so we're left with 2ar on the top. But on the bottom, we're going to make use of this. A is much, much smaller than R, so we can ignore this in comparison with this. So we've got R squared times R squared. Okay, so one of these R's will cancel with one of these R squareds. This 4 will cancel with this 2. And so we end up with Q over 2 pi epsilon naught, and we're left with A over R cubed. So that is what we were asked to show. So we've shown it for that case. Now the next case is very similar, so let's try and fit it on the same page. Let's just move this up here. R is a lot bigger than A. What we're going to do now is replace this minus Q with a plus Q. Okay, so the electric field, this part stays the same. We've got 1 over 4 pi epsilon naught Q over R minus A over 2 squared. But then this one becomes positive, so it's 1 over 4 pi epsilon naught Q over R plus A over 2 squared. Okay, so now adding those two together, we have Q over 4 pi epsilon naught R minus A over 2 squared, R plus A over 2 squared. Okay, we're just skipping this step and going right down to this, but we won't expand it. That's just too many steps all at once. So we've got R plus A over 2 squared plus R minus A over 2 squared. Now we need to expand up here, and we can make this same approximation here. So this is Q over 4 pi epsilon naught. Okay, expanding, we've got R squared plus RA plus A to the 4 on 4 plus R squared minus RA plus A to the 4 on 4 over R squared times R squared. So that's approximately. Okay, so in this case, these terms cancel. And now the A to the 4 is much smaller than R squared because R is much bigger than A. So let's ignore that one and ignore that one. So we end up with, this is approximately Q over 4 pi epsilon naught. Now we've got 2R squared left on the top and then R to the 4 on the bottom. So that will cancel, and this 2 will cancel. So we end up with Q over 2 pi epsilon naught times 1 over R squared. Now we're asked to comment on the different powers of R in the two cases. Well, this one is going to drop off much more rapidly with distance, and that's what we'd expect, because if we've got a positive and a negative next to each other, when you get quite a distance away, you're not going to see any charge at all. They'll kind of cancel each other out, and so you'd expect to have a very small electric field. If you have the two positive charges next to each other, then they're not cancelling each other out so much, and so it drops off just like a normal charge would, which has twice the charge. Okay, problem 7, which again is 1, 2, 3, 1 only. In this problem, we're given an arc. It subtends a total angle theta naught. So that angle in there is theta naught. It has a radius A and it has a charge Q spread along it. So the arc length is equal to A theta naught, and so the charge density lambda is equal to the charge over the length, so Q over A theta naught. What we're asked to find is the electric field here at the center. So we can write dE, the electric field due to a little increment here, is equal to 1 over 4 pi epsilon naught dq over the distance squared, which in this case is a squared. All these increments are a distance a from the center. But what we need to do now is we need to account for the direction, because these different increments are exerting electric fields in slightly different directions like that. Now what we need to do in this question is actually exploit the symmetry. So let's draw a line up the middle. So this angle in here is given by theta naught over 2. And if you consider these two sections, which are exactly opposite, when we draw their electric fields, they will be in this direction here. And you can see that the horizontal components of those electric fields will cancel each other out, but the vertical components along this bisecting line will actually add together. So let's let the angle between our bisector and our segment be phi. What we can say is all we want to do is add together these vertical components, the components along there. That's phi, then that's phi, and so we will need to times the electric field by cos phi to get just this length here. So the dE is equal to 1 over 4 pi epsilon naught dq over a squared times cos phi, and this is in direction parallel to the bisecting line. Okay, so what we need to do is just add together all these increments across the whole arc. So to do that, we're going to need to integrate. The electric field is equal to, now let's just do it for 1/2 from here to here and then double it to get the total electric field. So it's 2 times 1 over 4 pi epsilon naught. Now we'll be integrating from 0. We're integrating over phi, so phi goes from 0 up to theta on 2, theta naught on 2. And let's pull this one on a squared out the front, and then we've got cos phi dq. But let's look at what dq is in terms of phi. The charge is equal to the charge density times the length, which in this case is the arc length, so a theta. In this case it's a little increment of theta, so d theta. And now we're replacing our little increments d theta with d phi. So this is equal to lambda a. So lambda is q over a phi naught, a d phi. Our a's will cancel out and we end up with q over theta naught d phi. So we can replace this dq here with q over theta naught d phi. And now we can do this integration. So we've got 1 over 2 pi epsilon naught a squared. Let's pull the q and the theta naught out the front, and then we've got to integrate cos phi. When we integrate cos phi we get sine phi, and we're integrating from 0 to theta naught on 2. So sine of 0 is 0, so that part's easy. 1 over 2 pi epsilon naught a squared q over theta naught sine theta naught on 2. And that is what we were asked to find. That's the magnitude of the electric field. It's directed away from the arc and along the line which bisects the arc.